All right, second video of our topic set. If you remember, last video that we watched last night was on position, or I should say displacement versus distance. And we looked at how distance was a scalar quantity. We didn't care whether there was a direction associated with it or not. And then we had displacement, which was the vector form of that quantity, where we were always looking at how far away we are from the origin. Okay, so we looked at it in that sense. We're now moving from position, or from displacements and distances, into speeds and velocities. And again, we're going to see a similar follow through here with talks about scalar versus vector quantities, because they are, one is scalar and one is a vector. And we are going to look just from the average standpoint. So let's go ahead and get started with speed and velocity. All right, so now maybe we were out in the hallway and we wanted to collect some data. So we're gonna pick an origin, our frame of reference. And so we picked a spot on the floor and we said this is gonna be our 0 mark. So we're giving it an origin or a frame of reference. And then we're going to use a stopwatch and we're going to time ourselves as we're walking. So we start timing ourselves and we then pass various points. So like after 1 second we've made 5 meters, and after 2 seconds we've made 10 meters, and after 3 seconds we've made 15 meters, etc., etc. And we're collecting this data. So we're collecting two different variables. We've got a time variable and we've got a position variable, or a displacement variable, because we're measuring relative to the origin in this sense. What we like to do then is we like to create graphs to interpret the motion, okay? Because the graphs will tell us kind of a story behind what we're seeing happening here. So we got this first one is called a position time graph, okay? And we're basically graphing a position versus time. Time being our independent variable, so we like to put time on this axis, and I'm going to mark it with an S because we measured everything in seconds. And then we have our position here, okay, so this is our distance or displacement or our position. So I'm going to put position here, and it's measured in meters. Okay, and so we have these 2 points, and we're going to do an XY scatter. And so if you remember when we did the gum activity, we did a XY scatter where our dependent variable was time, or time chewed, and the mass of the gum then changed depending upon how long we chewed it. We're going to do the similar thing here with this one, and we're going to start where we have our points. And so I've got my nice little T-chart, and the first point I have is 0, 0. So I'm going to go ahead and I'm going to put a point here at 0, 0, and then I'm going to say, okay, so this is 0, this is 1, 2, 3, 4, 5, 6, okay, so that works out, and this is going to be now 5, and 10, and 20, and 30, and 40, and 50, no, wait, 5, 10, 15, excuse me, 15, 20, 25, and 30. All right, so we've scaled our graph. We're just going to plot some points. Now, typically we never do any of this by hand. We would have a computer do all of this. And in fact, when we get to our activities, you'll see that we'll use the computer extensively for creating these kinds of graphs. But this is, again, the background of where it comes from is by just taking points and plotting them just like we did in an algebra class. So now I'm going to plot my time 1 and a 5, and I got a 2 and a 10, I got a 3 and a 15 and a 4 and a 20 and a 5 and a 25 and a 6 and a 30. And so you can see I'm getting points that come out looking extremely nice in my opinion. I like to see straight lines. Remember, this is a direct relationship. As time was increasing, so was the distance, okay? So we got our thumbs up and we've checked it, and we know that it is a direct relationship, unlike our gum relationship was an indirect relationship. And now we're looking at this and we're going to say, this looks linear. Okay, if it looks linear, it must model something that looks like this: y equals mx plus b, right? That's our standard equation from algebra. And all that stuff that they taught us in algebra really plays well in physics, because that's why we learned so much of that stuff, was so that we could understand science. So we're looking at it in this sense, if I change some of my variables, position, depending upon the source, they like to use S's for some of it. So some book sources will use S to represent position. I tend to like to use a D. So I think of it in terms of a distance or a displacement. So I'm going to say, instead of using the letter Y, I'm going to use the D. And then I'm going to have this slope, okay? And instead of using X, I'm going to use a T. And my y-intercept apparently on this graph is 0, so I don't have to worry about the b. So I'm building a formula here, and I want to find out, what does this slope mean? So what does slope mean in this kind of a relationship? Now we can find slope, and we know how to find slope. It's the y's over the x's. So if I said, let's take my y positions, okay, over my x's, I'd take my y's, which was 30, okay, over minus 0 over 6 minus 0. So I'm taking this point here and this point here. I reduce that down, and I find that I get 30 over 6. Okay, 30 over 6 reduces down to 5. So I have a slope of 5. Okay, slope is 5. What's the units on my slope? Okay, and that was a question that I asked last time when we did this as a check question. And now I want to be careful. I want to look at what my units are based on my axes. So in other words, I have meters over here and I have seconds over here. This was in meters, this was in seconds. So I have 5 meters per second. Now when we start talking about things in meters per second, or a distance versus time type thing, a distance per time, we're looking at exactly what we should be looking at, which is a speed or a velocity. Okay, so we're building this thing and we're looking at it and say, with speed or velocity. So the slope in this case is equal to my, and I'm going to use a V to represent velocity, okay? And so that's going to be speed is equal to the velocity, or the slope is equal to the velocity. So now this slope of this line tells me kind of how fast am I changing my position, okay? So it's the rate that my position changes. Now, it is kind of considered an average. In fact, when you do averages in a math class, you're basically adding them up and dividing by the number, okay? And that's giving you essentially like a slope. It's a slope between 2 points. So that's kind of how we look at this, is the slope in this case is our speed, okay, or our velocity, and this line then represents the average speed or slope, or speed or velocity. So we're getting an average of that value over this. And we'll look at how the graph changes when we get to something else. Now, again, this is kind of how we're going to look at it. We're going to actually build a position time graph in class tomorrow using some little motorized cars. So that'll be something that we'll get a chance to look at. And we'll look at the slopes of those things. And see how different slopes impact or show different things. Now, again, this is how it comes out. It comes out looking like an equation to us. Our D is our Y, this is our M, this is our X. So in other words, it's a linear relationship. And we have now definitions for both speed and velocity and what the differences are. So speed is the time rate of motion. So in other words, as the distance changes per unit time, again, it's measured in meters per second. And velocity is the same thing as speed, but it's now defined in a particular direction. So in other words, speed is my scalar quantity and velocity is my vector quantity. Now, I do have a link to the They Might Be Giants song, and that's a good one to sit down and listen to after you're done watching the video, because it's kind of catchy, okay? And it talks about the differences between speed and velocity, and you'll be able to then remember that as well. This is nothing more than an easy little algebra problem for us to work with. So we can find if we have, say, an average. Sometimes I call this average, or we may refer to this as constant. So it might be a constant speed that we're going through. So if we're traveling at, say, 55 miles per hour, that's a constant rate for 5 hours. how far did we travel? That would be a question that could be asked. Maybe we're given a distance that we're going to go, like Mr. Anderson ran in a race on Sunday, and it was 5,000 meters, so I went 5,000 meters, and I don't know what my average velocity was, but I do know that I finished in, say, 23 minutes and 43 seconds. And so I should be able to figure out my V based on that. Let's go ahead and do that. And we'll determine what my rate was in meters per second. So I'm going to do a little unit conversion. I'm going to change this all into seconds. Okay, so I'm going to turn on my calculator. 23 times 60 gives me the number of seconds there. Add to that the 43 seconds. So it came out to be 5,000 meters is equal to V, and it's 1423 seconds. So I'm going to divide by 1423 seconds. So now I can find out what my V is. So if I take 5,000 divided by 1423, I find that I had an average of 3.5 meters per second. Okay? Now again, that's an average. Doesn't mean that I wasn't running faster than that or slower than that at some point in time. I can tell you that I was pushing a stroller. My son Cole was in the stroller, and when I was going uphill, I was probably going a lot slower than that, but when I was going downhill, I was probably going faster. So again, it's an average. Okay, if you had taken, you could have plotted my points for every, say, 1,000 meters, and we could have graphed it as well. But that's really how we deal with this in an equation sense. Okay, but it's nothing more than a linear relationship. The one thing that I want to do here is I want to look at position time graphs and some various things that we could look at. You can see the green one has a nice slope. Okay, it's a fairly steep slope, and as steeper the slope we get, that just means that we're traveling at a faster rate, because a bigger slope is a bigger speed or a bigger velocity. You can see here that we have this graph here, we had a steady slope, okay, so it looks like a steady speed, but then all of a sudden we got to a point where we have a flat spot in our graph. Now the flat spot tells me that I'm not changing my position any, but time still ticks on. So really, what am I doing at that point in time? I'm standing still, okay? So I was running for a while, and then all of a sudden I stopped because I probably had to wait for the traffic light to go, and then maybe I decided that I needed to, go back home. So again, you can see that I'm running now at where my position is actually going back towards the origin. So this is a return back to the start. So when I look at this graph, this one that I started here in the red, my displacement was 0. I didn't move from my displacement. I ended right where I began, but my distance covered would be represented more by how much distance did I go out here. There no distance change here, but then I had some distance that I came back, so it was like going out and back. Now the blue line is kind of a more interesting one because it's not a straight line, and that's where we're going to get into looking at our slopes. And this one, it says getting faster. So in other words, if I said from here to here, on the average, my slope looks like that. It's a slow slope. But from here to here, at this point in time, the slope increased a little bit. So I got a little bit more of a slope. And from here to here, I got a little bit more of a slope. And then from points here to here, I got a little bit more slope. So the slope was changing. And that changing slope says that I'm changing my speed. Okay, and that'll be a key thing when we get to some of the stuff further on. Again, when we start to look at a graph, every graph tells a story, and that's kind of the key thing, is we're going to start to look at graphs and be able to interpret the motion based on that. I only have about 30 seconds, so I'm going to tell my little story very quickly here. It must have been a nice sunny day, and I decided to leave school, and I was out walking away from the school, and at some point in time I got down to the intersection and I had to stop, and I stood and waited. I crossed the intersection after the light changed, and then I decided to start walking away. But then I forgot at some point in time I needed to go back And so I headed back to the intersection, but then I got picked up in a car, and so my graph ended. There you go. Speed